Alexei,
yeah,
he was saying hi to everyone.
yes. I saw that.
Hello.
So yeah, let me make short for the slides. It's easy to read. I will show updates on a couple of works in collaboration with those people, essentially the 3D spin group in Pavia and the focus scientist in Pisano, about unpolarized quark TMDs, about their extraction, about some problems that we stumbled upon while extracting TMDs, and prospects, which means also the possible impact on hadron colliders of our findings. So let's start with part one. So past, present, and future of an almost global fit. Why is it almost global fit? Because the Pavia fit is based only on semi-inclusive elastic scattering and production, and not only plus and minus manipulation, which is one of the next directions we plan to explore. Of course, I don't need to recall you the basic facts about semi-inclusive deep elastic scattering, nor I need to describe Charlian Protestant and Z production. So I will move directly to the selection of results of previous fits. Here you have the columns of experimental measurements: Hermes, Compass, Drellian, mainly coming from Tivatron, and Z production coming from Tivatron and from LHC in the near future. No, the data are still there. In the near future, we are including in the future in the fit this data. And the first column contains the framework for the fit, which means the accuracy of the contributions in the W functions. So next to log leading order means that the Wilson coefficients are leading order, and the A1, A2, and B1, B2 coefficients are next to log in the sort of exponent. Where there is no evolution, it means that this fit has been data have been fitted separately for collaboration, so there is no evolution over square of the theoretical contributions. And where you see next to log, next to order, this is the most advanced. Next to log, next to order, this is most advanced from theory point of view that you can reach at present for this kind of fits. Our fit, the Pavia 2017 fit, includes all available data except for the plus and minus data, as I've already said, and contains is performed with the framework next to log leading order. So leading order with coefficients, and next to log with pseudo exponents. I wish I could write here Pavia 2018 for the update of this fit, but realistically it will be a 2019. And the framework will be next to in order, next to in log, so the Wilson coefficients will be at next to in order, and we will include LHC data for C production. Fitting the hadron multiplicities means fitting this quantity, the multiplicity, so the ratio of the hadronic, the production of the hadron H normalized to the inclusive deep elastic cross-section. And you have the complete formula, which is this one. But if we want to stay well in the TMD factorization region, this term vanishes, because when Q squared is much greater than M squared, the hadronic mass scale, and when PhD squared is much less than Q squared, this term vanishes. And at the present accuracy that we are exploring, that we have explored in the last fit, this term only starts at higher contribution of alpha S. So basically all we have in the for hadron multiplicity is this function, it's FUUT, unpolarized photon in unpolarized target with a transverse photon exchange, transversely polarized photon exchange. The formula, the complete formula for the FUUT would be this one, with the TMD PDFs, with the TMD fragmentation functions, and with the hard factor, which at present accuracy is order alpha S to the 0, so it's a constant, it's order 1. And the matching, the asymptotic term minus pixel order expansion, which at present, which we are not including here. So we are confining ourselves to the region of low QT in such a way to only explore the W function and not matching with the perturbative contribution.
Did you break?
Okay.
Let's thank the speaker again.
Let's try. Sorry. Let's try to. What?
So since you are break, so I'm kind of annoyed because you didn't include our rate.
Is that why the laptop is not working?
Yeah, I guess.
That's why you have your laptop on and you're interfering with it. Okay.
Yeah. We have the matching. Actually, we cover out the white I mean, of course, we fixed the only.
Oh, wow. Because I tried before, it wasn't responding. Okay.
Yes.
So
That's
Maybe you just go back.
let's just go to the
You
next.
just go back and see whether it works. Might just be
Or just start again.
I understand that, but all the global phase right
Works.
now is why
Takes an experimentalist.
because the idea on why the analysis doesn't work at low Q. We point out this mistake in our paper, and we propose a new functional form for the non-breaking part. That's in our paper. I think all the recent development is based on our calculations.
The reason was only that one. I was only focusing on global fit, but I will add it in future slide.
It's unfair for us because we spent a couple of years working on this.
Okay.
No, I mean, and always ignore. I don't know why.
From now on, every talk he gives, if he doesn't mention it, we're going to do the same to the computer.
Okay. The computer is changed.
Okay. Same story for Drelian. So in the TMD factorization region, this second form factor vanishes. Let's say it does not contribute, and we only have the W term, so no matching, order 1 for the hard factor, and two TMDs here. So as for the evolution of TMDs, of course the evolution is performed in the BT space or CT space. You will find CT and BT mixed in the next slides. Whenever you see BT or CT, is the transverse momentum, is the conjugate variable to transverse momentum. And the complete formula in the B space is this one, where you have perturbative computable factors, for instance, the Wilson coefficients, the pseudo form factor, and you have non-perturbative parts extracting from data, parameterized and extracted from data, which are collinear PDF, the non-perturbative part of the evolution, and the parameterization of the intrinsic KT that you have to provide. And here starts the part where I describe a little bit our model. This is the parameterization of the intrinsic KT that we used in the last version of the FIT. And in the case, both for TMD-PDS and TMD-FFs, you have the weighted sum of two Gaussian contributions with the same width for TMD-PDF, this G1, and different widths of TMD-FFs, so G3 and G4. Here you have a sample of these two Gaussian. The first one is this one, the second is this one, and the sum of the two has this shape. Okay? This choice is inspired by some model calculation that we will find as a reference here. Then you have the non-perturbative part of the evolution, as I was already saying in the previous formula, and this is customarily written like this. So we just chose the easiest form, let's say, but of course other functional forms have to be explored, and we are currently exploring them. In total, when you add this parameters and this G2 parameter, you have 11 free parameters in our flavor independent scenario. I say flavor independent because in principle, of course, this could depend on the flavor A of the part on contributing in the process, but we did a flavor independent fit. So for the moment, we only have 11 free parameters. A large part of the theoretical investigation has been devoted to the B integration, which is, of course, a well-known problem use in this kind of studies. Basically, you don't have to go to high values of p, because otherwise you cross the Landau hole. So you have to place a cutoff. This is a possible choice and was the original choice of the CSS formalism as well, with the B-star prescription and the max fixed. But you don't want to go to lower values of p as well, because lower values of p means high values of t, and presummation and TMD factorization is not valid anymore when you have high values of t, so the lower values of p. So here, either you put a b-min prescription, so you cut off your integral at some b-min, or you resort to other schemes, for instance, the complex B integration, which was proposed at the beginning of 2000, or I mean, there are many procedures that have been proposed to overcome these problems. We chose to propose this functional form for the b hat, let's say, variable, which behaves like this. You have a b max, which is, oh, sorry, these are interchanged. This is b max and this is b min. B max is 2 times e to the minus gamma Euler, and the b min is 2 times e to the minus gamma Eulers over q, in such a way that our integral, our W integral, is always from 1 to q. Our variable is always from 1 GeV to q, integration variable, and in such a way that for most of the integration region, b hat is equal to bt. So this is almost a straight line here, and it saturates rapidly to b min and b max. Okay. Of course, this is a crucial point from both for the theory point of view and for the phenomenology, especially of SIDIS. And as I said, other possibilities are there for integrating over the B variable, and we are also exploring how dependent are our results from these other possibilities, these other prescriptions.
But was the B star
similar to this part, but not to this part.
No, yes, that was for the large.
Yeah, but this is inspired by B star.
So is it essentially the?
Is it essentially the same B star, but modified in such a way that you don't go to B equals 0, essentially?
Yeah, that's the difference. Yes.
Yes.
Okay. But for the large B, it's
for the large B is basically essentially the same. Yes. There is also the +1 prescription, as of course you know, for the B equals 0, for removing the B equals 0.
And how does that differ from yours? That's the participatron, so
the +1?
The +1, the logarithm 1 plus.
Bozzi deflorenzi. This is +1 prescription.
Is it the same that
the shifting on
shifting
didn't shift the log. The argument of the log didn't shift. There was a shift. And this mimics the +1 prescription, but of course it's not the same, because you definitely have a cutoff, while we don't have cutoff. The +1 prescription introduces the so-called resummation scheme, because you could switch not by 1 but by A. So this introduces automatically a resummation scale that you have to take.
But for small b, actually, there's no particular issue. So I don't see the rational.
The rationale is that you have to recover the collinear factorization and the collinear cross-section at high QT.
Because you always have to match.
The matching is switched off, because at some point the result contribution becomes negative, and so you have to switch it off.
Yeah. So I mean, the TMD is TMD. So in a sense, you don't have to really match the collinear, because TMD resum to all orders. TMD is resum to all orders. If you really want to get this collinear, you also have to work on all orders. You can.
And if you don't use that prescription, you're in the integral on the cusp, then the lower limit can become larger than the upper limit. So
That's
basically absorb the gluons instead of radiating.
That's fine, because that will cause any practical problem. I mean, this has been practiced, for example, for many years.
Okay, but would you call it natural?
Oh, yeah. Because you adopt by on and off. And Alexei was Berkeley a couple of years ago. He raised this question. I said, for the TMD, in practice, it's not a problem. I mean, you can't do this. You have some argument to support this idea. But I mean, for example, in our field, we don't have that. It works.
You are fitting only.
You are fitting on relevant data.
If you go to SIDIS, then the life is.
You have to, if you want evolution, if you want your
so if you talk about SIDIS, then we have a whole talk about it, right? We know this by turn. You cannot use the TMD at all.
Well, for compass, you mean?
Not on compass, on this too. There's Y turn. I mean, this is a famous result. I've talked about this a couple years ago. Exact here. There's Y1 contribution. I mean, you cannot really seriously talk about SIDIS right now, unless you have very high Q score. Right? I'm not talking about this.
If you try to reproduce LHC data, you need some prescription to switch.
No, you don't. You don't. We can describe every state data of Observables or whatever. That's in the response.
When you go to a QT 50, 60, or 70, or 100 GB,
that's a fixed order. You don't.
How do you switch?
Well, this matching. You have the intermediate transform region. You switch to the continuum calculation.
I mean, go with switch. You mean switch like
yeah.
Ah, okay. Okay. We are not switching by hand. I mean, switching by hand is something. Switching with a coherent picture is another thing.
No. Okay. So even in soft continuum effect theory, there's a different way to do that. There's a soft matching, the hard matching. I don't know what the risk was. I mean, at one stage, CP told me that in soft switch, that's fine. In soft continuum effect theory, you also have to have this sort of matching between the TMD and the continuum. But at 50 G, you definitely have to rely on continuum calculation. You don't rely on the TMD at all. I mean, even for that, you don't have Y term here. How you talk about this?
No, in this study, but I've worked on this for 15 years, so I know.
Okay. I know. So that's the exact point. So in the 50 T, you don't need the TMD at all, right?
Yes, but we're trying our best to minimize the by hand stuff. I mean, we want a coherent picture, and we want this coherent picture to work smoothly for any energy. This is the effort we're putting in.
So that's okay. It's okay, but if you don't have Y term, you cannot talk about this.
Okay, in this particular place.
Right.
Okay. Shall I move on? Great. So, experimental data. These are the experimental data we used. So, compass, vast majority of experimental data, with a recent update in March 2018 with more than 2,000 new data points, and it's in progress for this new data. The first stage of the fit was performed with those 6,000 points, which makes a grand total of 8,000 data points. Work in progress is also for CMS, ATLAS, and LHCb, and these are tough because the experimental errors for these guys are really small. This is really a task for global fit. This is the XQ square distribution of data. I will skip it because you all know. And these are our data selection for SIDIS. We want to make sure that we are well inside the TMD factorization region, and we want to make sure that we avoid target fragmentation and exclusive contribution from low Z and high Z. So these are our selection cuts that leaves this number of points after cuts for Hermes and for Compass here. For Compass, there was a problem with previous version of data. It was a normalization problem. And to overcome this normalization problems, we normalized the observable to the first spin of the provided data in such a way to that the R fit was independent of this problem. For Drelian and Zeta and Z, sorry, we had a cut on QT because since we don't have the whiter, we have to make sure that we are in low QT region, and so we excluded QT greater than 0.2 Q plus 0.5 GV, and these are the number of points that are left. So for our almost global fit, the pros are that it is an almost global fit, okay? It includes the evolution. I don't have the time to talk about replica fitting methodology, but we use replicas to perform this chi-square fit. We have a kinematic dependence for intrinsic AT, but we have no flavor dependence, and we are going beyond Gaussian assumption for intrinsic AT. On the contrary, we don't have E plus E minus data, so we don't have pure information of perturbation functions. We have correlated information between TMD effects and TMDs. The accuracy of TMD evolution is not the state of the art, it's leading order and extreme log, but we are working on it. We don't have the fixed order, we don't have the whiter, but we are working on it. So we will plan to extend our region also to intermediate and high QT regions. And we have no flavor dependence. I cannot say we are working on it, but I can say that we are thinking about it. So, this is the agreement between data and theory. The overall quality of the fit is quite good because it's 1.55 chi-squared of degrees of freedom. We have problems at low z for the multiplicities of Hermes into pi plus. As you see, the values of the fit are quite high. We have kaons behaving better than pions because they have larger uncertainties. We have larger uncertainties from perturbation functions. And we have compass, which behaves better than Hermes because they have a huge number of points and the normalization helps. And to this respect, the normalization, the observables we have normalized helps the convergence of the fit.
So can I ask you a question about the lows? I mean, what's a bit surprising to me that you get the C cuts the same as Hermes and compass. The W is different from the two expressions. So you would think for compass you can have a larger Z range than for Hermes.
Mm-hmm.
I didn't expect more of that for Hermes. If you pick, for say, for compass 0.2 to for Hermes 0.2 to 0.7, I wouldn't have expected for compass it would be bigger. And because both more or less the target region fragmentation gets squeezed more in one corner and the exclusive gets squeezed more. So that you have problems at low C for Hermes is not too surprising. Isn't it true? I mean, you would expect different Z ranges, I would think. Okay, so anyway, because it depends on W, essentially. Yes. Right. Well,
Right.
Yeah.
Right. This is the, let's say, correlation plot between QT squared and PT squared, together with previous analysis of the same variables. The red region is our fit. As you can see, the inclusion of Drelli and NZ with respect to the other studies in this figure diminishes the correlations. This blob is a little bit expanded than the lines that you see from other fits. The inclusion of compass, which is not included here, increases the average transverse momental QT and reduces its spread. And possibly E plus E minus data would further reduce correlation. But for the moment, the situation is this, like this. Here you have a sample of the average transfer momentum for TMD-PDF and TMD-FF as a function of X, just to give you the shape of this observable. Finally, we tried to investigate the stability of our results. These are our best chi-squared, 1.55. We tried to normalize Hermes data as we did for compass, and the chi-squared suddenly goes to 1.27. So this proves the fact that normalization is one of the reasons behind the better behavior of compass data than with respect to Hermes data. Then we also changed collinear PDFs. We used NLO GJR 2008 as our default choice. We tried MSTW and CJ12, and the fit slightly deteriorates, goes to 1.84 and 1.85, but nothing dramatic, let's say. And finally, we chose more stringent cuts to make even more sure that we are in the TMD factorization region. So we Q squared greater than 1.5, Z from 0.25, 0.6, and PhD less than 0.2 QZ, and chi-square is almost 1, but the number of data is 477. It's not 8,000 anymore. Okay, to conclude the first part, and I hope not my entire talk, We tried this first global extraction of TMDs from SIDIS, dy, and z. We were able to test it.
9 moments.
9. Okay. Okay.
Not the second.
This to test we had the opportunity to test the universality and evolution from rays of partial TMDs, and we investigated 8,000 data points. What's the future? Additional data. We hope in the future to include also plus and minus, more flexible code because up now the code is not that optimized, let's say, and higher accuracy, including higher order, either pseudocode and in the Y term. Okay, second part, stumbling into unexpected problems. While looking at Tevatron data for Drellian and low Q square and high QT, we stumbled into really unexpected problems. And I'm talking about these experiments, R209 at CERN and all these experiments at Tevatron. This is the reaction, this is the year of data taking. And here you have the information about the fact that these experiments were included in TMD feeds or in PDF feeds. Okay, the square root of S is between 20 and 60 GeV for this experiment. And please remember the fact that we are talking about experiments included in PDF feeds. So these data are used. Of course, I don't have to explain you that to describe the transverse momentum spectra, you need the W and Y term. This is the asymptotic, this is the fixed order, and this is the Y term. In this region, so in the low QT, you should rely entirely on the W term. In this region, you should rely entirely on fixed order linear factorization, or at most with supplementing it with the matching. Okay. But this is the situation. When you go and see R209 at CERN, these are data, and this is the pure fixed order result, and next to in order alpha S squared. Okay. Here you have the asymptotic term. When the asymptotic term vanishes, this signals the onset of the purely collinear region. So from here on, you have to rely entirely on fixed order results. And as you can see, you cannot. Here you have the scale uncertainty at leading order alpha S of the fixed order, at next to in order alpha S squared. As you can see, scale variation doesn't help solving this problem. This is the ratio data minus theory over theory. So the difference between data and theory normalized to theory. You have almost a factor of 2 everywhere in the validity region, and also a factor of 5 and higher. Okay. This is E866. Again, next to in order plus PDF uncertainty. We changed PDF here, and the variation is like this. Please have a look at the logarithmic scale. So these are very far from theory. And here you have scale uncertainty. Again, we're not on data at all. Here you have still 8866, and you have the ratio data minus theory over theory. Bad. Really bad. This is from here on, you should rely on fixed order, and fixed order is a factor of 7. Okay. E288, same story. I will skip because I mean you have a lot of results that really look the same. What did we try? Well, with Werner we tried to. You basically cannot try anything because a factor of 5 or factor of 7 or factor of 10 is not curable in any sensible way. But before giving up, we tried almost everything. We tried threshold resummation together with Vogelsang. Threshold resummation provide a 10–20% on top of the next in order alpha S squared, but of course is not capable to cure this disease. And this disease was already known in the past because in 2005 it showed up for E706 experiments as well. There's the paper from Werner and Daniel de Florian, and logarithmic scale. So here you don't see it clearly, but you have the same problem here, same non-agreement between data and theory. And we were so desperate that we tried also to provide by hand an intrinsic KT. So we throw an intrinsic KT in the collinear PDF and see what happens. Of course, this cannot work because the intrinsic KT cannot have an impact at large QT. And as you can see, this is the intrinsic KT, and it approaches the next in order as you go higher on QT. So conclusions, I don't have conclusions. I can only say that fixed order perturbative QCD largely underestimates low energy Treelian data at high QT. Neither threshold resummation nor intrinsic KT seem to help. We are trying to explore more high QT data. We're trying to look at Phoenix at the moment. Phoenix seems to behave better, but Phoenix is also a little bit inside the TMD region than the collinear factorization region. So we are moderately excited by the Phoenix agreement. Please, any help, hint, comment, or suggestion is desperately welcome. So if you have ideas right now, give us some idea, because we are not able to understand it effectively. Just really, I promise I will be really fast on the impact on precision measurements at the LHC, and I will show you the WMAS case. At hadron colliders, you have observables and pseudo-observables. Observables are easy because you can count them. Okay, cross-sections and asymmetries are easy. You count your events, and that's your measurement. Pseudo-observables are functions of cross-section and asymmetry. For instance, WMAS, the Z mass, and thus they require a model to be properly defined. So to measure MZ at LEP, you actually measured a Bright-Bickner resonance factor. So you have to provide templates for this Bright-Bickner resonance factor, and then put these templates on data. Same thing happens for MW. MW is measured as a fitting parameter of a template fit procedure. What is a template fit? A template fit is a procedure where you generate several histograms with the highest available theoretical accuracy and the highest available description of the detector, and let the fit parameter, for instance MW, vary in a range. Then you put this histogram on the data, and the histogram that best describes data selects the preferred WMAS. And this is the measured WMAS. This is a template fit. Of course, the result of a template fit depends on what you choose to compute the templates, PDFs, scales, non-perturbative, different frustrations, and all these hypotheses should be treated as theoretical systematics. Okay, you can use this template fit technique also from a purely theoretical point of view. If you want to estimate an uncertainty coming, for instance, from PDF, different choice of PDF, you can use this template fit procedure. I show just an example of this paper from a long time ago, where we wanted to estimate the impact of changing PDFs on the WMAS measurements. And so we produced several templates with same PDF, CTEX 6.6, and different values of NW, 348, 349, 350. And then we produced a set of pseudo data with a fixed value of NW, 8398, and different PDF sets. Then we performed the chi-square between pseudo data and templates. Of course, the pseudo data had low statistics and template had high statistics, because otherwise you cannot conclude anything from the chi-square fit. And the template that best describes the pseudo data defines the shift induced by the change of PDFs. Of course, if you use the same PDF here and here, you have to find the central value. Of course, okay. So this defines a shift, an error. Okay, WMAS. These are the observables used for the measurement of the WMAS. They are the transverse mass defined here, the lepton PT, and the missing energy, missing transverse energy. The MW is extracted from the study of these shapes, and the Jacobian peak that here is smeared from detector smearing effects, let's say, enhances the sensitivity to MW, because in this region, this would be the theoretical prediction without smearing effects from the detector. And in this region, as in all regions at the edge of the phase space, you have multiple emissions of gluons. And this is really sensitive to higher order QCD effects. As you can see, for the transverse mass, the theoretical predictions without PTW modeling and with PTW modeling are almost the same. This means with PTW modeling, of course, I mean soft Galois resummation and higher perturbative effects that give rise to the PT of the W. And for the lepton PT, the PTW modeling is really important, okay, because it extremely modifies the shape of the lepton PT observables. So I anticipate a large effect of PTW modeling on lepton PT and a moderate effect of PTW modeling on the transverse mass. And this is what actually happens, because here, if you see, these are two different distributions from MT and lepton PT, differing by 10 MeV in the W mass. This is the ratio. 10 MeV effects is a 7 per mil effect here, and 10 MeV effects is a 0.5 per mil effect, if I'm not right. If I'm not wrong, okay? So, yeah, if I'm not right, 0.5 per mil effect is a crazy effect. I mean, this means that if you hope to measure MW with a precision lower than 10 MeV, you need to control your experimental measurements at better than 0.5 per mil. Okay, this is crazy. This means that this is a really difficult measurement. Okay, and all possible of theoretical uncertainties can contribute to this observable. Okay, and so you really have to tune your simulation. You really have to investigate better and better possible sources of uncertainties for these observables. These are the quoted uncertainties from various experiments. For a transverse mass, CDF quotes 3 MeV uncertainties for lepton PT. PDF uncertainties is 10. And 9 for lepton PT. This is what I was saying. Lepton PT is much more sensitive than transverse mass. Okay. The 0 quotes 2 and 5. Yes. Atlas quotes 3 and 3.4, but Atlas cheats because Atlas restricts the window of lepton PT, and so restricts also the possible uncertainty in NW from PTW. Okay, so what did we do? Since PTW depends on QCD initial state radiation, and since up to now the intrinsic KT effects are measured on Z data and then used to predict W distribution, but Z and W have different flavor structure and have different phase space available, of course we suggest to use different Gaussian factors for different flavors in such a way that what is good for Z is not as good for W, because they have different initial states. So this universality that is currently used in hadron collider experiments is not motivated, and we're trying to prove that it's not motivated. So what we did is a really preliminary exploration, let's say. It's the easiest thing that we could do. You all know very well that there is this prefactor, the famous non-perturbative contribution to evolution that we talked about before. This G value has been fitted by many people, and its value is more or less 0.8 G squared. So what you can do is assign 0.4 to each quark in the initial state in such a way that you recover this 0.8 and vary this 0.4 to take into account a possible flavor dependence of this effect. So considering U valence, D valence, UC, DC, and all the rest, we tried to vary around 0.4 this non-perturbative factor, okay? And we created 50 flavor-dependent sets around this central value of the flavor-independent set of 0.4, more or less randomly, with between 0.2 and 0.6, this factor, okay? Then what did we do? We tried to understand which of these flavor dependent sets were Z equivalent. What do I mean by Z equivalent? We produced a PT spectrum with the flavor independent set. We put experimental error bars for each of these pseudo data points, let's say, and then we generate 50 PTZ spectrum with the 50 flavor dependent sets and select by a chi-square procedure among these 50 flavor dependent sets those that were Z equivalent, so equivalent in a chi-square sense. Okay, so those for which the PT spectrum is undistinguishable from the flavor independent set. Okay, then we take this flavor dependent Z equivalent sets and treat them as our pseudo data. We take the flavor independent set and treat it as our template, and we perform the exercises before, the chi-square fit between pseudo data and template. This is the result. No, sorry, these are the sets and these are the results for the shift. Of course, as you can see, there are sets that do not shift at all. MW, 0, 0, at least MW plus, MW minus is moderate shift, but there are also sets that shifts by 9 MeV in the case of lepton PT, the central value of MW, minus 6 central value of MW. And let's see, as an overall comment, for what concerns the transverse mass, you have 0 few MeV shifts, and in general, they favors lower values for W minus. And this is preferred by electroweak fit, because electroweak fit would prefer lower values for the W minus. And in the case of lepton PT, the shifts are quite important. For instance, in set 3, 9 MeV, and the envelope, if you consider set 2 and set 3 is 15 MeV. And so we think that this is an evidence of the fact that you cannot perform a flavor blind analysis anymore, but you have in some way to include flavor in your high precision measurement because of the fact that the impact is comparable, for instance, to the PDF. As you have seen, the PDF uncertainty quoted was 10 MeV, here you have 9. So it is a comparable effect to that of the PDF. So no flavor blind analysis should be allowed anymore. For the future, we are planning and we are currently studying possible flavor effects on W mass at LHCb. This will be interesting because LHCb is an asymmetric kinematics. So you have very forward parton and very different values of X, and this may have an effect on our analysis. And of course, we are planning to investigate, we are planning to investigate also charge current and unit current ratios. For instance, PTW over PTZ. This is a very important observable because PTW over PTZ is used by experimental correlation to tune the real measurement of PTW. And so predicting with high accuracy PTW of PTZ is essential for W mass measurement. I think I abused a lot of you. So
you overused your time. Yep.
5 minutes questions.
Yeah.
Just a couple of questions. The first question is on the first part of your talk.
Mm-hmm.
You said you looked at the sensitivity if you change the collinear PDFs.
Mm-hmm.
So what about changing fragmentation?
We didn't do
are more uncertain.
Yeah, you're right. But we didn't do it. We still didn't. It was doing it in the recent weeks, but I'm not sure. No. At some point, we thought about using neural network representation functions, but we didn't do it yet. But yes, of course, it should be done.
And concerning the W mass, maybe I missed it. What is currently the official error that is quoted for the W mass?
Overall?
Yeah.
No, you didn't miss it, but I skipped it. That's it. It's 12 MeV, and the global electroweak fit is 8 MeV, and this sets the goal for experimentalists. I mean, the experimental collaboration are working hard to make this 12 reach that 8, and they are also blaming us not being too good. The modeling uncertainties we currently dominate the overall uncertainty and W uncertainties that would need to be reduced. So they are really blaming us, and this is a
Anyone else? I have one, maybe perhaps very naive question on the problem with the Dralion. Why have we never seen that in the approach of Hannes Hume? Because they are doing similar things in their unintegrated PDFs. Hannes Hume and other people. They also look, I think, at the same data. Why don't we see it there? I've never seen this Dralion problem. Should they have seen it too? I don't care.
It's I think it's inclusive concept. They don't look at.
I see. They all look inclusive. Yeah. Anyone else? We might even have a little bit over 20 minutes coffee break. 11 a.m. Thank you again. Exactly what I want to add.
Ma questo è ancora qua. This is still here.
That